we'll understand the difference between a vector and a scalar quantity. All right, related but not the same. We're going to be able to use the proper notation to express concepts involving vectors. And we're going to be able to represent vector quantities using a coordinate system. There are two ways if we talk about algebraic vectors and geometric vectors. So we're going to be looking at the difference between those two representations of vectors. One uses the coordinate system and one does not. Okay, let me go past that. Definition. A vector is a quantity, as you just heard from the clip, that has both magnitude and direction, right? A scalar quantity only has magnitude. So let's try to make a distinction between the things that are scalar and the things that are vectors. So scalar would be like distance, right? To go from here to there, let's say Kerry lives 6 kilometers from University of Waterloo. That's just distance, right? That's all that is. So that's magnitude. How far apart are they is just a measure of magnitude. Speed, although some people think it's the same as velocity, it is not, because speed is just the magnitude of the change in position over time. So a plane is traveling at a speed of 852 kilometers per hour. If that's all you're saying, if all you're giving is the speed it's going at, right, then it means that it is a scalar, because all you're talking about is the size of that change in position over time. Mass is also a scalar. Mr. Ford, and I'm not referring to anybody in particular, no politician whatsoever, just happen to use the name Ford, has a mass of 100 kilograms. So again, that's just the amount of the mass of Mr. Ford. On the other hand, what would be considered vectors would be displacement. So not only are you saying that Ken or Kerry lives 6 kilometers from University of Waterloo, you're also telling the person in what direction Kerry lives in relation to University of Waterloo. This says northeast of University of Waterloo. So when you add that component to it, now you're moving from a scalar to a vector. So the two things again are related, but the fact is that you have to add another dimension to the distance in order to make it a vector quantity. All right. So if you want to give a vector quantity, you have to give both the direction and the distance together for it to be a vector quantity. And then also velocity as compared to speed, although people use them interchangeably, they're not to be used interchangeably, because in strict mathematical terms, velocity is a vector quantity, because not only are you saying the person is changing their position relative to time at a certain rate, but you're also saying in what direction that person is moving. So that's what velocity is. And then when we use the term velocity in this course, we're going to be talking about it as because a vector quantity, not speed, which is just a scalar. And then weight now takes a component of the mass and gives it also a direction. So if we said that Mr. Ford has a weight of 980 newtons, that is telling you the force with which he is pushing downwards towards the earth, okay? Based on, yes, the mass has something to do with that, but you have to add the component of the direction in which that force, that weight is being exerted, and that is what weight is. That's why weight is a vector quantity, whereas mass is just a scalar quantity. So hopefully that distinction makes sense. Vectors are usually represented in one of two ways, right? And you need to be comfortable with both ways. You can either use an uppercase letter that signifies the beginning and end of the vector. And you would see, for instance, this AB that I'm pointing to here, where the vector is basically going from A to B. So the arrow on top is giving you the direction in which the vector is actually, as we just said, direction matters, right? So this arrow on top tells you direction that the vector is going. It starts off at A, so there's some point in space that we're calling A, and it ends up at B. So there's some distance that A goes towards B, but also there's a particular direction in which that goes. So the AB vector is not the same as the BA vector, for instance. The arrow would be pointing the other way. So one lowercase letter can also be used with a vector symbol across it, a vector or an arrow symbol above it. So I can use a lowercase with a single letter to represent a vector. And we'll be seeing both of those as we go along. So either uppercase with 2 letters and the arrow on top, or lowercase with the arrow on top. Both of those could represent vectors, which again represent both direction and magnitude. Okay? When we identify a vector as A, B, the initial point is A, so it starts at A, and the ending point is B. And we refer to A as the tail of the vector and A as the head of the vector. So it goes from the tail to the head. I've heard people use other terms which are similar. Tip. Sometimes you hear people talking about the tip of the vector, which is the same thing as the head of the vector. So you'll hear that term sometimes. If you go to the University of Waterloo website, you'll hear them talking about the tip of the vector, which is the head of the vector. Okay? All right, so we can use these rays, these arrows, to represent vectors. So you'll see, for instance, an arrow which is going from A to B. So again, that would mean that we're talking about uppercase A to B. And you can see that the arrow is pointing in this direction, which means it's going in a northeast direction. Of course, you know, north is straight up, east is to the right. So northeast is somewhere in between those two. So this is tail to tip. I just talked about tip as being another way to put this, to say head of the vector. And you can also represent the same vector with that lowercase u that we just talked about. All right. So here's another vector, which is the BA vector. So even though the lines seem to be running the same way, parallel to each other, they're not going in the same direction, because the B represents now the tail of the vector, and A now represents the tip of the vector, or the head of the vector. So this vector is actually running from B to A, which is what this is saying down here. So it has the same magnitude, 200 kilometers per hour, but whereas this one was northeast, this one is actually going southwest. So they're not the same vectors, right? In fact, we're going to be calling these opposite vectors in a little while. All right, so the magnitude of a vector is symbolized using an absolute value sign. And you've seen these before in math. If you put these two lines around something, like what you see me pointing to right here, that means that I'm asking you for the magnitude of the vector, or the size of the vector. How long is the vector? How big is the vector? Right now, I'm not caring about the direction of the vector. I'm only asking for the magnitude. So that's what it means when you see these lines around the vector, which we normally refer to as absolute values signs. And a magnitude, by the way, can never be negative. Right? Just make sure that you understand that magnitude is a size of something. You never talk about negative length, for instance. So, or never talk about negative mass, for instance. So when you're looking at the size of the vector, then you always have a positive answer for that. So two vectors can be equal if and only if their magnitudes are the same and the direction is the same. So if vectors have the same direction and the same magnitude, then they're regarded as being equal vectors. But they're opposite, and I used that term a few minutes ago. If their magnitudes are the same, so they have the same distance, but their directions are opposite, right? So like in the case of the one I showed you before, these are two opposite vectors here, all right? All right, so in this case, they're denoted as the negative of the other one. So negative in front of a vector means that the vector that you are putting negative in front of is turning the vector going in the opposite direction, is all we're saying. So if A is equal to minus B, it means that these two vectors are opposites of each other. They have the same exact magnitude. So the size of A, the magnitude of A is equal to the size of B, but they're running in opposite directions. That's all that means. Okay, so if A is equal to minus B, then A and B are opposites. Two vectors are parallel if the directions are the same or opposite. So does parallel always mean that they're going to be, also the same magnitude? No, two vectors can be parallel, but they're not necessarily opposites of each other, right? Okay, now I want you to look at these vectors right here, several vectors, an A to B vector, which is 3 centimeters long. Remember again that the direction of each of these things matters, all right? So what we're going to do now is ask the question, which vectors are equal? So let me throw that over to you, right? If you see these lines and you see what the directions are and you see what the magnitudes are, can you give me any pair of vectors which you consider to be equal? Here's where I look for input from the class. AB and ML is what I'm hearing. I'm hearing that from Vanessa, I'm hearing that from Adam, I'm hearing that from Fernando, Kushi, Anika. AB and ML is absolutely correct. Absolutely correct. So here's the AB vector running from A to B. Here's the ML vector running from M to L. They're both 3 centimeters long. So that makes them both equal vectors. Notice they're not in the same place, right? Vectors don't need to be in the same place to be equal, right? This vector is up here in space. This one is down here in space. But that doesn't stop them from being equal. They have the same magnitude, they're running in the same direction, and they're therefore equal. Okay, are there any other equal vectors that you can see there? Any other equal vectors apart from the ones that you just gave me, A, B, and ML? Anybody see any other equal vectors? No? Don't see any others? All right. Are there any opposite vectors that you can see? Okay, I'm seeing CD and EF. I'm seeing AB and FE. So it looks like there's more than one opposite vector. And I'm going to agree with you. AB and FE are definitely opposite vectors. So AB runs in this direction. FE runs in, and don't say EF because EF is not the same thing as FE, right? It runs from F to E. Look at the direction of the vector, right? And we also are looking at two other vectors. That's FE and ML. So FE runs from F to E, and this one and is 3 centimeters long, and ML runs from M to L and is also 3 centimeters long. Both are running exactly opposite directions from each other. ML and AB. Let's see if that makes sense. ML and, well, ML and AB are the ones that we said were equal here. Remember Kushi? Does that make sense? ML and AB, ML, AB. They're both equal vectors, but the opposite ones are the ones that we're looking for right now. Okay. And again, thank you very much for that input. I prefer you giving input that may not be right. I mean, that's okay because correction is getting corrected is part of learning, right? It's the people who just sit there and not say anything that doesn't work as well. Okay. So thank you very much, Kushi, for that input. Okay. So those are the equal, those are the opposite ones. Which ones are parallel is my next question, right? And which ones, let's go with parallel first. Give me any pairs of parallel vectors. Just parallel. What is it? Parallel, and you know what parallel means because you've done this back in, I guess you'd have taught with parallel from elementary school. Give me some pairs of parallel vectors now, please. Anything that's parallel, right? So AB and JK, AB and JK. Okay, anything else? Anything else, Ariana and Tomaleo? So AB and ML. Okay, good. FE and ML. FE and, yeah, I'm going to agree with all of those answers. And ML and JK, ML and JK. I'm going to agree with all of those answers. Right? So AB, ML, FE. And the ones that are of equal magnitude would be AB, right? Equal magnitude means that they have the same magnitude, but they don't necessarily have the same direction. So AB, so this one here, ML, FE, right? And CD. Now, they don't all run in the same direction, but they are in fact magnitude equal. They're the same size is what we're saying. And by the way, I'll also take your answer, Kushi and Tomaleo, of JK being parallel. Yes. Although it's not said here, I agree that those are parallel to the AB, the ML, and the FE. Okay? So yes, I'm going to agree with those answers. All right. So, oh, by the way, JK and GH are also equal magnitude. I forgot to mention that. So this vector here, GH, and this vector here, JK, not equal direction, but equal magnitude. Okay? All right, geometric vectors and algebraic vectors. What is the difference between those two types of vectors? We'll do them both in this course, but we need to make a distinction between them. So vectors which are referenced without using a coordinate system, like what we just did, those geometric vectors that we just used, didn't really need a coordinate system, right? Those are geometric vectors. Algebraic vectors which are referenced within a coordinate system. So if a vector's tail is at, I forget that I can't use the wheel of the mouse because that makes it go forward and back. If a vector's tail is at 3, 5, and the head is at 5, 1, refer to the vector as AB, and its magnitude is denoted by, and we said this before, the 2 lines around it, and it equals the square root of 20. How do I get that? By using the distance formula. The square root of 20, or 2 root 5, that is. The magnitude of a vector is never negative. I said this before because it refers to the size only, not the direction of the vector. So if you're putting it within a coordinate system and you give the 2 points 3, 5 and 5, 1 as being the head and the tail of the vector, then it's very easy to use a distance formula. You know how to find the distance between 2 points from when you were in grade 10, right? So the distance between the x's, 3 and 5, 3 minus 5, and you square that, plus the distance between the y's, 5 and 1, and you square that, you add them together, and the square root of that would represent the magnitude of the vector that runs from A to B. So it's pretty easy to figure out that magnitude if you just simply use a distance formula that you learn in grade 10. All right, and I made the point again that it's never negative because it refers to the size only, not the direction of the vector. That's the algebraic vectors that I reference within a coordinate system. We also have geometric vectors which do not use a coordinate system. Directional bearings are very, very important. We're going to have a lot of questions that have to do with directional bearings, and those of you who are doing vectors will probably go on to careers that include have something to do with direction, right? So for instance, pilots who are charting a course between two cities, clearly, I mean, if the pilot is any good, has some notion about directional bearings, okay? So what direction should he be flying in or she be flying in order to get from point A to point B? Clearly, that is part of how this works. Now, I should tell you, and of course, those of you who have done some work with vectors before know this already, that a large component of vectors is based on trigonometry, right? So if you struggle with trigonometry, you know, your SOHCAHTOAs and your, you know, all that good stuff, the sine law, the cosine law, you're going to have to brush up on that stuff because that comes in and factors into this course big time, big time. Anyway, vector mathematics is used to apply to problems. So there are lots of practical applications for vectors in everyday life. And two of the commonly accepted ones are for directional bearing. So I want to sort of go over with you the way that you would give a bearing, meaning a distance that you are moving in. So if you look at what's on the diagram here, you'll see that this is one way to give a directional bearing. So you will have two letters. So this says southeast. This is saying, as you look at the diagram, you'll see what this is trying to say. This is saying that you are 34 degrees east of south. Okay, so here's south down here, right? And you're moving east from south. You always put the north-south first, right? And then you put the east-west. Most people do, I should say that, because I've seen it done the other way as well. And then you put the east-west second. So you're taking the north-south as the starting point, and you're saying you are, in this case, 34 degrees east of south, right? Is one way to express where you are. And if you can look at the diagram, you see what I mean by that. So you start off at south and you move 34 degrees to the east of that. As you know, east is on the right, west is on the left. Hopefully you know that. Hopefully you remember that. And north is up and south is down. So that's what 34 degrees east of south means. So for example, south 61 west means direction is 61 degrees to the west of due south. So if I put this over here, right, where I'm pointing to right now, then I could put a 61-degree angle in between those two, and that would be south 61 west. So that's one way that you can represent bearings. The other way is to measure an angle starting off from north and going in a clockwise direction. So from north, if north is regarded as 0, then as you go clockwise from there, so here's an example of 241 degrees. 241 degrees means you've gone past 180 and you're now in this quadrant down here, which would be like your southwest quadrant, all right? So you can give that as an angle of 241, right? But you can also give this angle in the same way that we gave the one before, which is you could give this as a south some number west of south, okay? Because you're on the western side of south, so you could do that way as well. So as it says here, use from 0 to 360, and you indicate the direction as measured from due north. In this case, you could say 140 would be the same as south 38 east, and I'll show you what I mean by that. I'll just show you what I mean by that. So this is 0 up here. So 142 would be somewhere down here. This angle in here would be the 142, right? Measuring from north. But then if you think about it, that would be the same thing as 38 degrees from down here. All right, measuring that, remembering that a straight line is 180 degrees. And you notice that, by the way, we've gone back to using degrees. For some reason, radians are not very popular in vectors. We tend to work almost exclusively in degrees. So this would be what we just said, south 38 east. All right, so you are 38 degrees east of south is what that means. Okay, and of course, this one could also be given as being a southwest bearing. If you figure out how far you are in this direction here, that would give you a southwest reading. All right. Okay, connecting vectors to two-dimensional figures. Here's a rhombus, and I remind you what a rhombus is. A rhombus is, sometimes people call it a square. So in a rhombus, all the sides are actually the same, right? But it's not like a rectangle or a square where you have 90-degree, well, you can have 90-degree corners, but you don't need to have a 90-degree corner if it's a rhombus. So this rhombus has all of these sides the same. So A to B, B to C, C to D, and all of these sides are actually the same. So if this rhombus is drawn and it has two diagonals, so here's a diagonal running from here to here, AC and BD, right? So B to D, those are two diagonals that are drawn. Name the vectors equal to each of the following. So let's see how well we do with this. Let's start off with a vector that is equal to AB. Look at the AB vector. Now remember, A necessarily means you're going from A to B, right? And not the other way around. So which vector would be the same as the AB vector? Over to you now, folks. Your time. Give me a vector that's equal to the AB vector, running from A to B. All right, I'm looking for reaction from you at this point. Okay, I'm getting the DC vector from a whole bunch of people. Let me acknowledge them. From Anika, from Jordan, from Kushi, from Sarah, from Ashvan, from Taj, from Kushi, and that is absolutely correct. It is in fact the DC vector. All right. How about the dA vector? Give me a vector which is the same. Remember, if it's going to be the same, then it must be both the same direction and the magnitude. So how about the dA vector? What is the equivalent to the dA vector? All right. I see one answer there already. I see BC and I see CB. You know, which one is correct? All right. Is Kushi correct or is everybody else wrong? I'm just trying to figure that out, all right? Because she said B to C. So remember, we're trying to go from D to A, D to A. So is it B to C or C to B? Okay, all right. So it is in fact C to B, all right? Because you have to go in the same direction. So from D to A means you have to go from C to B, all right? Okay, hope everybody, yeah, good. All right, how about the EB vector? E to B vector. What's another vector which would be the same thing as the E to B vector? I see some DEs coming in there, right? And I really appreciate those who are participating. So Adam, Ashvan, Carly, Jordan, Fernando, Tomileo, and Ariana. And for once, everybody's on the same page, right? It's a DE vector. And finally, the AE vector. Give me something that's equivalent to the AE vector. Thanks, Ashran. Thanks, excuse me, Vanessa, Fernando, Tomileo. The EC vector is correct. Yes. All right. Well, it's fairly straightforward because all we're looking for is another line that is the same magnitude. Remember, if it's a rhombus, then all the sides are the same, right? And all you're looking for now is the ones that are parallel to those vectors. Okay. So draw a vector to represent the displacement of a box moved 12 meters up a ramp, which is inclined at 30 degrees to the horizontal. Well, I'll show you what that looks like. So here's the line that would, and I probably should have made that thicker. Here's the line that represents the ground. 30 degrees to the ground would look something like that. So that's the 12-meter line right there. And there's my 30-degree angle right there. So the vector that represents the displacement of a box, the box is moving along this line right here, right? It's being moved 12 meters up a ramp, and it gives you not only how far it's being moved, it also gives you the direction in which it is going, 30 degrees to the horizontal. So there is a vector quantity right there, right? There's your A, there's your B. So the AB vector is that. Okay, let's get to this one. Now, there's a little bit, you have to be very careful with this one, but let's see how well we do with it. MNOP, the rectangle, has side lengths 3 and 5. Q is the midpoint of MP. All right, so Q right here splits MP exactly in half. All right, so there's 2.5 on either side of that. So fairly straightforward so far. 3 centimeters, these two sides, right? Rectangles, it means that you have two equal sides, actually two sets of equal sides. And this one is 5 and one is split in half to give you 2.5 on either side of that. Find the angle between the following vectors. Now, when you hear angle between vectors, I want you to make sure you understand that we always measure angles between vectors when they are tail to tail. That's an important point to remember. You must place vectors tail to tail if you want to measure the angle between them. So it says NP and NO. Let's look at where NP is. NP is this line right here, and NO is this line right here. They're already tail to tail, right? So if you go from N to P and from N to O, they're both starting from N. So it should be fairly easy for us to find what that angle is. We're talking about this angle right inside here. But let me just show you what angle we're talking about. We're looking for this angle right up in here. So how would we find that angle? Can you help me out with that, please? Right, that angle between NP and NO. Can you give me a suggestion? 90 over 2. You mean 45 is what you're thinking? 45 degrees, Ashfan? Yeah. If this was a square, I would agree with you. But you're thinking that this angle splits the right angle exactly in half. But I don't think that's true. I don't think that's true. So I understand your reasoning behind it. And if it was a square, I would agree with. If all the sides were the same, then yes, that diagonal would split the angle exactly in half. Is there another way that we can look at this? Opposite angle equals 90, Kushi says. Opposite angle equals 90. Okay. So you mean the angle up top here is 90 degrees? This one up here is 90 degrees? That's the one you're thinking about, Kushi? Or I'm not sure which one you're calling 90. Find the hypotenuse. Do we need the hypotenuse for that? I'm thinking we don't really need a hypotenuse. 9 over 3. Aren't triangles 180? Yeah, that's true. So there's a right angle right here. Okay, but I haven't heard anybody say it yet. Sokotoa, thank you very much. Some opposite angles. Okay, I hear that, Kushi. But can we not use Sokotoa to find this? Tomalea just said that. Is there something we can use right now out of Sokoto that can give us the size of that angle? Right? In fact, what I'm going to do is I'm going to erase the other angles that we put on. And thank you very much for all that input, by the way. But I'm going to erase these because I think we really need to focus on this angle right there. That's what I think. Right? Tan. Oh, look at you, Sarah. Look at you. Shouldn't we just use tan? That the tan of that angle should be equal to opposite over adjacent. What Tamalea is saying the same thing, right? Well, I'm going to agree with that. Okay, where's my pen thing now? Take off, there we go. I'm going to agree with that. The tan of theta, if we're calling this theta, is equal to 3 over 5, isn't it? Okay, so work out what that is for me now, please. Everybody remember that from, I don't know, grade 10, I guess? Right? Go ahead and work out what that angle is now. What is the size of theta? Everybody, get your calculators. Folks, you got your calculators close by. Get your calculators out. Let's figure out what the size of this angle theta is. Right? So theta is this angle right up inside here. That's the angle between the two vectors. And opposite to that is 3. Adjacent to that is 5. So the tan of theta is 3 over 5. Okay, so Fernando is saying 31 degrees. And Tash agrees. There you go, folks. And of course, I expect you all to be able to do that and know that you have to use the inverse key to be able to get that angle. That shouldn't be difficult for you. You all have calculators, should be scientific calculators, and therefore that's the answer. Okay, let's get to the next one. Thank you very much, by the way. Thanks for all of that. Thanks. I appreciate all of that input. Even if the persons didn't get it right the first time, I want to make sure that everybody follows what we just did. All right. So let me check in with Ashvan on that. Ashvan has really been very vocal. Actually, Ashvan gave me the answer. So why should I be asking Ashvan? Let me check in with somebody else on that. Fernando, Danny, how about you? Does that process make sense to you? What we just did using the tan ratio for that? Does that make sense to Danny? What do you say, Danny? Where's Danny? Where is Danny? Earth to Danny. Need to hear from you, Danny. Where are you? Okay. Not sure where Danny is. All right, I'm not getting the right answer in my calculator. Oh, you know why that might be? You might be in radian mode. You might want to check the mode of the calculator and make sure you're not in radian mode. I know many times we tend to think that radians is the way to go, but in this occasion, we need to be in degree mode. So you know how to change yours, Ariana, back to to degrees. And if you change it back and you're still not getting it, I look it up. Okay. Is everybody else getting the 31 degrees? And where's Danny? By the way, still looking for Danny. Where's Danny? No Danny. Danny is missing in action. All right. Is everybody else getting the 31 degrees? And everybody understands why we're using that as the way to do it. Kashaf, how about you? Thanks, Jordan. Thanks, Sarah. Thanks, Carly. Kashaf, your Kashaf is good. Okay. Still asking for Danny. Still looking for Danny. No Danny. All right. So let's continue. The angle between NM and NQ. So let's take these away. Let's take that away. And in fact, let me erase this thing here because we're now looking for a different angle. Hold on a second. Okay, so now looking for a different angle. Danny, yeah, I'm here. Sorry, the bell was at my door. Okay, Gaia, Danny, got to stay with us. All right. So let's get to the next one now. Let's get to the next one. NM and NQ. So NM is that one, NQ is that one. So what do you think, folks? Now that we've kind of got the hang of this, we're trying to find the angle in between those two. And again, they're both starting from N. So we're getting the angle in between them, right about here. There's our theta. What are we going to use this time? Okay, so props to you. Anyway, get the angle for me, please. What is the size of that angle? Go ahead right now on your calculators. It is tan again, but now it's 2.5, which is the opposite side over the adjacent side. What's the size of this angle? And again, I apologize for not getting it this time. So I'm getting 39.8 from Danny. Ashvan agrees, and I'm going to say it's approximately 40, which is about right. Yes, good. Okay, let's get back to it. I'm not going to try to do attendance because it's still not working. So I'm assuming the people who I marked absent before are still absent. I should just do a quick check though. The people who I marked absent before were, hold on a second, no, were Zach, Alexander, and Jessica. Can you let me know whether any of those people are here with me now? Zach says I was here. When I did attendance before, I don't remember you saying you were here. All right, I'll put you down as being here, but I don't recall that you responded when I asked the first time. Okay, all right. How about the other two people, Jessica and Alexander? Are they now here with us? No? Okay, all right. Okay, let's get back into it. Let's get back into it. So we found out, in fact, I can go back just a little bit here, right? Tan of 3/5 we figured out was for this angle that we had, 31 degrees. And now we're supposed to be working on this angle. And I mistakenly said it wasn't tan, but yes, it is in fact tan. And we worked that out to be 40 degrees. Okay? Now, let's get to the last one. The last one says NQ and QP. Now, there's something different about that one. Does anybody notice anything different about that question? So I know you can easily figure out where NQ is. In fact, it's still on the board right now. And you can easily figure out what QP is. But what's different about this question when you compare it to the ones that we have done so far? Can anybody see a difference? When you see, look at the two that we just did, the NP and the NO, the NM and the NQ, it's not a triangle. Well, it can be, sort of. NQ, let me just trace that out. Where's my thing here? NQ is this line right here. Is that not working? Hang on. NQ is this line right here, and the QP is this line right here. So you could make the argument that it's not. Ah, look at that. Not tail to tail. Well done, Sarah. The initial points are not the same. Thank you, Thomas. Very good observation. That was the case for all the others that we did. But this question says find the angle between the two vectors. So if we take this as being NQ and this as being QP, then the angle between them is not the angle that we have right here. That's not the case. So let's look at this one carefully. There's your NQ, right? There's your QP, but we're not dealing with the angle between them because the angle between them is supposed to be when they are tail to tail. So how do we solve this? Well, here's how we solve this. We're going to use this angle down, this vector down here to represent the QP vector. And what I've done is this vector runs from N to the midpoint of the NO line, right? Because remember, as long as the two vectors have the same distance, the same magnitude, which is 2.5 in this case, and the same direction, they're equal vectors. So I'm representing the QP vector with the N to the midpoint of this vector down here, right? Now, if I did that, then the two vectors would now be tail to tail, right? Does everybody see what I'm saying here? So I want to check in with the room on that. Does that make sense? That I can represent the QP vector with another vector that runs in the same direction and has the same length. But it's now in a position which puts it tail to tail with the NQ vector. All right. Does that make sense to the room? I just want to get a sense of whether everybody sees that. Tash says yes, and Vanessa and Tomale. Okay, perfect. All right. So we're going to change our perspective. We're going to find the angle that's down here between those two lines. So what angle am I talking about? This angle right here. That's the angle I'm going to be trying to find. And to get that angle, and I put a representation of it down here, excuse me, we're going to be using, first of all, Pythagoras' theorem to figure out what the NQ line is, because we need this line. Actually, the truth is that we could have used this line right here, now that I think about it, and we could have used the tan all over again. But one way that we could have done it is also to find the length of this line. We know the length of this line is 2.5, and that works out to be this. And then we can use cosine. But the truth is, we could have used tan again. And I'm not sure why I even went through all of this with the Pythagorean theorem, because we can actually use the length of this line as being 2.5, the length of this line as being 3, and we'd get the same answer as using the cosine over here. At any rate, what is the size of that angle? It would be approximately 50 degrees. Okay, this is using cosine, but the truth is we would have used the opposite and adjacent again, the 3 over the 5, which will give us the same answer. Okay, all right, so the important point to remember is that a lot of people would have thought it was this angle up top here, right? We thought the angle that we're looking for is this angle up here, but it's not, because you have to get the two vectors to be tail to tail. So whenever you're looking for an angle between vectors or an angle is quoted between two vectors, always consider that angle to be angle measured when the two vectors are placed tail to tail. Okay, so that's why that's 50 degrees, and you can confirm that either using this way of doing it or taking the tan to the -1 of 3 over 5. Okay, so that's what that side there is, and still 50 degrees. And actually, I'm showing it to you this way as well, 3 over 2.5. Over 2.5, I said 3 over 5, it's actually 3 over 2.5, sorry, not over 5, 3 over 2.5, so it gives us the 50 degrees. So, can we move along now? Everybody fine with that? I said 3 over 5, it's not 3 over, 3 over 2.5, because this side here is half of the 5 line up top here. So both will work. and both give you the same answer. Okay, so we're going to finish up the first class of vectors by just going through these success criteria. You can identify vector quantities and scalar quantities. You know the difference between them both. I can recognize when they're equal, they're parallel, when they're opposite, and you can determine the magnitude of geometric and algebraic vectors. So that is what that is all about.